Good morning. Today we're going to be talking about Dalton's law of partial pressures. So Dalton's law tells us that the total pressure of a mixture of gases is equal to the sum of all the pressures of the gases in that mixture. So our formula is P total, so the total pressure in the system is equal to P1 plus P2. Notice these are addition, so plus P2, P3, and I have Pn because we can have an infinite number of gases in the system. So these are partial pressures. So if I was given the gases in this room, I would have P total for the total pressure in this room. And notice that these numbers, they're arbitrary. They're being assigned to whatever I want to assign them. So if I was finding the total pressure in the room, I would say P nitrogen because most of the atmosphere is made of nitrogen, plus I'm exhaling carbon dioxide, so I've probably got some carbon dioxide. So I'd find the partial pressure of carbon dioxide. Plus I have plants in my room, so I'd have the partial pressure of oxygen. They're giving off some oxygen. Plus I've probably got some argon in here, plus some other trace gases. Alright, so I would find the partial pressure of each one of those, add them all together for the total pressure of my system. So we're going to do some practice problems for Dalton's law. They're going to start off easy and get a little harder as we go. Alright, the first problem. What is the total pressure in a canister that contains nitrogen gas at a partial pressure of 904 atmospheres, hydrogen at a partial pressure of 320 atmospheres, and oxygen at a partial pressure of 540 atmospheres. So a couple of things about this problem before we get started. First of all, I'm finding the total pressure. I'm finding P total. Okay? Another thing to make a note of is that all of my pressures are nicely lined up, but also they're all in the same pressure unit, so I don't have to make any conversions, which is really nice because we might have to do that at some point. But you want to make sure that all of your pressures are in the same unit before you try and add them up. If you're adding pressures that are in different units, that won't work. Alright, so your pressures have to be in the same unit, and in this problem they are. So I'm going to set up my formula. So it says that I have nitrogen gas at a partial pressure, so I'm going to have P nitrogen. And you'll notice that I'm putting N2. That's because when nitrogen gas by itself, it's a diatomic. So I have PN2 plus hydrogen. Hydrogen is also a diatomic, so I have PH2 plus oxygen. Oxygen is one of our diatomics as well, so I have PO2. So here's my formula. And now it gave me each one of these. I can go ahead and plug them in. So I'm going to have 904 ATM. Make sure you keep your units throughout. PH2 is 320 plus 554. Add those all together. And it should be noticed, this would be a really, really, really high pressure. Atmospheric pressure or normal pressure is about 1 atmosphere. So we would have 1,778 ATM is equal to P total. Alright, so that was a pretty easy problem. We're going to move on to another slightly more difficult problem. Alright, this problem says a flask contains 3 noble gases and has a total pressure of 1.87 atmospheres, a little bit more normal pressure. What is the partial pressure of krypton in the flask if it also contains neon at a partial pressure of 0.77 and helium at partial pressure of 0.62 atmospheres? All right, so we're going to set up our formula again. P total. And we know that the total pressure of our flask contains 3 noble gases. Our 3 noble gases are, so we're trying to find the partial pressure of krypton. This is our question mark. Okay. And then it says neon has a partial pressure of 0.77 and helium has a partial pressure of 0.62. So krypton plus the partial pressure of neon plus helium at 0.62. All right. Now, before I actually go to put some numbers in and solve this equation, I like to solve using variables. So I'm trying to solve for krypton. I need to get the partial pressure of krypton by itself. In order to do that, I'm going to subtract the partial pressures of neon and helium from both sides. That'll get me the partial pressure of krypton by itself. So they're going to cancel out. And I've rearranged my formula to get the partial pressure of krypton is equal to P total. And now I know all of the things on the right-hand side of the equation. So I can solve directly for the partial pressure of krypton. And now I can look to my question and plug everything in. So the P total is 1.87 atmospheres. And if you'll look, before I actually go to plug everything in, everything is in atmospheres. Just like we talked about on the last problem, everything is in atmospheres, so I don't need to make any conversions. So I have 1.87 atmospheres minus 0.77 atmospheres minus 0.62 atmospheres. So the partial pressure of krypton will be 0.48 atmospheres. We've got one problem left to do. This problem will get a little bit more difficult. So our last problem says, what is the partial pressure of nitrogen gas in atmospheres in a container if the total pressure of the container is 1 atmosphere? All right. The container also contains oxygen gas at 380 millimeters of mercury, argon at 27.35 kPa. So, a couple things to note before we get started. I'm given 3 different units of air pressure. My 1 ATM is my P total. My 380 millimeters of mercury is my P oxygen. And my 27.35 is my P argon. But they are all different units of air pressure. So, my problem tells me what it wants me to convert to. It wants me to convert to atmospheres to get the partial pressure of nitrogen. So I'm going to set up my problem. P total is equal to P nitrogen plus P oxygen plus P argon. Then over here, I'm going to write P total, and I'm just going to write down all of the things that I'm given in case I need to convert anything. I don't need to convert my P total because it's in the unit that the question is asked me for. My partial pressure of nitrogen is what I'm looking for. The partial pressure of oxygen is 380 millimeters of mercury. And the partial pressure of argon is 27.35 kPa. My video from yesterday shows you how to convert. And if you forget, it is on the front of your reference packet under standard pressures right here. So the first conversion we're going to make is oxygen. We need to get oxygen into atmospheres, so I'm going to use my conversion factor of 760 millimeters of mercury to every 1 atmosphere. And when I make that conversion, 380 times 1 over 760, I get 0.5 atmospheres. And then my next conversion I need to do is from kPa to atmospheres. Notice I'm trying to get everything into atmospheres just like the last 2 problems we did. Now, if you're doing a problem in the future, it doesn't have to be in atmospheres. That just is what this problem specifically asked for. In order to convert kPa to atmospheres, the conversion factor is 101.3 kPa every 1 atmosphere. And I get 0.269, so I'm gonna round that to 0.2718. All right, now I have all the numbers that I need in order to go into my equation. Just like the last problem, I don't want to plug straight into my equation, but I instead want to rearrange it so that I have nitrogen by itself, because that's what I'm solving for. So I'm going to subtract from both sides. And get my formula so that I have P nitrogen by itself. And now my equation looks like this. I can go ahead and plug everything in. P total minus PO2 minus PAR, or P argon. So my P total was 1 atmosphere. Minus the partial pressure of oxygen was 0.5. Minus the partial pressure of argon is 0.27. So the partial pressure of nitrogen will be equal to 0.23. And we're finished.